All right, so in an effort to save a little bit of time, the formulas that I provide you today, we're not going to get too in-depth with the proofs of them. As I said, if I have time later this week at some point, if I can make some videos, I'll do that to go through those proofs. I do think seeing proofs of this stuff, just in general, and the things that we talk about in high school algebra, is beneficial to you as you move on to other courses. You might get into a calculus course in college where you are doing some proofs, and having a little bit of a background, or at least an understanding of what you're doing, or the purpose of the proof, or just proofs in general, I think is beneficial. I think if you're thrown into a course that is a lot of proof work, it might be kind of a shell shock. Okay. When I was in high school, it was just kind of a lot of stuff was given to us. A lot of facts were given to us. We didn't really work through the theory or the logic of them with proofs. And then when I got to a college-based course in which I didn't have a whole lot of experience with proofs other than geometric proofs, it was kind of, like I said, shell shock, and it took a lot of work to kind of get my head wrapped around things. But I think hopefully the way I've designed the class to see, periodically a couple proofs every once in a while gives you an idea of what what involvement proofs have in collegiate courses. Because at that point, when you're doing math at the college level, you're not interested in what an account or an investment has in it after 4 years. You're not doing those types of calculations anymore. You're investigating how properties and laws interact and work off of one another, and we do that through, obviously, proofs then. Getting into geometric sequences, we'll talk about sequences and series today. Just remember that the difference between them is that a sequence is just a list of objects. A series is taking that list, and instead of connecting them with commas, we connect them with plus signs or minus signs. We can add them or subtract them. Usually, we're just going to be adding them, and if their terms become opposite, it turns into subtraction, right? But a lot of times you'll see geometric sequences kind of bounce back and forth between a plus, a minus, a plus, a minus. We see, I think, that a couple times today. But every geometric sequence is going to be of the form. We talk about arithmetic as being repetitive addition, right? Geometric, then, is repetitive multiplication, okay? And if you think about it, if I think about arithmetic as repetitive addition, but that common difference is negative, I'm doing repetitive subtraction, right? Okay. Well, here, if my multiplication is a number between 0 and 1, okay, and it doesn't really have to be between 0 and 1. It could just be maybe a 4/3 or something like that. If my common ratio incorporates a rational number that is not an integer, okay, then I'm doing ultimately a little bit of division. Does that make sense? So if my ratio, just to show maybe the most obvious, if my ratio is like 1/2, I am now doing repetitive division, because multiplying by 1/2 is the same thing as dividing, right? Okay. So arithmetic sequences are all about adding and subtracting something from each term to get the next one, and geometric is repetitively multiplying or dividing by the same amount to get the next terms. Okay. So we see that every one of them is going to have the form of A being your first term, A is your first term, okay? Then to get the next one, you're going to take A and you're going to multiply it by R, your common ratio. Then to get the next one, you're going to take A times R times R. I'm going to write that R squared. Then we take the third one and multiply it by R again to get the fourth. Take the fourth, multiply it by R again to get the fifth, and we keep doing that, right? Well, remember, this is your first object. That's the first thing in your list. That's n equals 1. Here, n is 2. Here, n is 3, 4, 5. Okay? Now, I could write this, and I'll do it this way. R, A times R to the 0 would be another way of writing this first term, right? How does, just like yesterday when we talked about arithmetic sequences, how does that exponent relate to the position? How many multiples of R am I using? It's one less, right? Okay. So what we come up with is this rule that says this is going to keep going. We'll have A times R, whatever n is out here. Let's say n is n. Then this number of R's that I have in here would be n minus 1. Does that make sense? Okay. So that's how we generate that basic rule for a geometric sequence. Okay. And then R, obviously based off the sequence, can be anything. Okay. And we'll talk about how we determine R here in a moment. All right, so here we've got a sequence that's being generated by A equals 3 and R equals 2. So they give you that information. I want to look at that sequence, and basically they're taking A sub n equals A sub 1 R to the n minus 1, and they're taking 3 and then getting 3 times 2, and then 3 times 2 times 2, and then 3 times 2 times 2 times 2, and so forth all the way through. I want to make sure that when we evaluate that and get a list of 3, 6, 12, 24, 48, that we can work our way backwards and make sure that that sequence was generated by an A value of 3 and an R value of 2. So I want this is kind of the common practice that your web assignment homework is going to talk about. If this is my sequence, if this is what I have, okay, kind of ignore starting off with that stuff. They give me this sequence, and at the onset, I have to decide what kind of sequence is it. Is there a general pattern? We look for arithmetic, and we look for geometric. Those are the first two things that we do. If they're not those things, then we're going to have a little bit of an issue of coming up with a rule. But what we do to find whether it's, obviously, it's not arithmetic, because when I subtract those, I get 3. I subtract those, I get 6, 12, 24, right? Common difference is not the same. So the next thing I do is I check to see if they are arithmetic, or no, sorry, geometric. If they're geometric, R is going to be found by dividing successive terms, okay? And this is kind of the way you do it. You take A sub n, so you take your nth term, and you're going to divide it by the n minus 1 term, okay? Now, if that is my common ratio, that needs to be something that has to be true. It has to be the same quotient for all n's, okay? So what I mean by that is that I have to start at some position in my list, okay? Now, if I want to use A sub n minus 1, A sub n minus 1 means the prior term, right? Does that make sense? The one before. Well, if I start here with A sub n, is there a prior term to divide it by? No, okay? So I always have to start, when doing a geometric comparison, I'm going to start with the second term and then divide by the one before it. Does that make sense? That rate, to be a common ratio, that ratio needs to exist between all terms in my sequence. So now I'm going to look at this one. Okay, take 12. What's the preceding term to that? Yeah, 6. If A sub n is 12, then A sub n minus 1 would be 6. Was that equal to the same thing as 6/3? Yeah. Now I've got to do 24 and compare it to its preceding. 24 over 12. Is that still the same as 6/3? And I do 48 over the one preceding it. Be 24. So all those R values equate to be 2, right? Because each one of those is 2. We have a common ratio. You will see, when you do this every once in a while, you'll see that you get a common ratio 2. You see one of 2. You see one of 2. And then here, this one will be like 36. And now 36 divided by 24 is not 2 anymore, right? So then it would not be geometric. But they get you kind of, I think, in that mindset. Well, I checked those two. I checked those two. They were both the same. I'm good to go. You got to check all of them that are in the list that you're provided. Is that all right? Okay. So R is 2. A sub 1 is indeed 3. So then we'll say A sub n, that rule, remember, is always A1 times R to the n minus 1. So A1 for us was 3 times then R, which is 2, raised to the n minus 1. That is the rule that's going to allow us to get any one of those terms. And if you think about it, let n be 1. You get 3. If n is 1, you'll get 3 times 2 to the 0. What's that give me? 3. If n is 2, I'm going to get 3 times 2. N minus 1 would be 2 minus 1, right? That's just 1. What's 3 times 2? 6. If n is 3, 3 times 2 to 3 minus 1. Now I got to do 2 squared first, right? 2 squared is 4 times 3, 12. N is 4. We get the same thing here. See this pattern, hopefully. So now I got 2 cubed, right? 2 cubed is 8 times 3, 24. Okay. And then obviously we'll put 5 and then we'll get the 48 that was in that sequence. Is that okay? All right. Do a couple more of these. That sequence, guys, is that kind of narrow as I progress through that list? Is that going to start narrowing down to one particular value? No, the values start getting larger and larger and larger, right? So that sequence, you guys remember the words that we would use for that sequence if it doesn't approach one particular value? What's a word for not meeting or not divergent, okay? So that sequence would be considered a diverging sequence, okay? Let's look at this one. Okay, the sequence 2, negative 10, 5, negative 250, 1250. You see here that it's jumping back between positive and negatives, right? Okay. Well, if you're jumping back between positive and negatives, there has to be something that does that. Okay, if you think about it, when you take a negative and you raise it to the first power, you get a negative, right? Negative to the second power turns into a positive, right? Negative to the third power goes back to negative. Negative to the fourth power goes back to positive. So it's the exponent being even or odd, okay, that's taking this negative value and making it positive or negative, okay? So there should be a negative aspect in our R here that is creating the plus or minus aspect of the list. So if I look at this number, that's A sub n, and we'll compare it to A sub, wrote that wrong, A sub n, we'll compare it to A sub n minus 1, that should give me my R value, right? We go negative 10 compared to 2. Is that then the same thing as 50 compared to the one before it of negative 10? Is that then the same thing as negative 250 compared to the one before it of 50? The same as that one, 1250 compared to negative 250. What do these all equate to? Negative 5, right? Okay. A lot of times in your geometric, they don't want you to kind of spend a lot of time dividing all these. If you got geometric sequence, a lot of times they give you like the first 3 terms, maybe the first 4 terms, so that you don't have to do all that repetitive division to make sure that R is constant. But now, finding A sub n, we have A sub 1 times R to the n minus 1. So A sub 1 would have been 2 for this one. R is negative 5 raised to the n minus 1. That negative 5, raising it to some power, that power is going to initially be 0. Okay, so it's going to be a positive number, right? That makes sense? Give me this positive 2. And then when it's squared, okay, or I guess the second term would be power of 1. So that's going to be an odd amount. -5 to the first is negative. But when I go to the third term, this becomes squared. So negative squared is a positive, right? Okay. And we keep going back and forth to get positive, negative, positive, negative, positive, negative, because of how we raise that -5 to an exponent. If I wanted the list to look a little bit different, what could I, if I wanted that sequence to start with a -2 and then go to +10 and then -50 and then +250 and then -1 or 1,250, where would I add another negative in front of a 2, right? Okay. You would still see, obviously, in that list, you would still see a -5 as my R. Does that make sense? Because you'd have a +10 divided by a -2. You have a -50 divided by a +10. You're still getting a -5 for R, but because a sub 1 was negative, we put a negative out in front of that 2, and that will start with a negative in that sequence then. If they ask you this, and once you have that, okay, you got that rule for the sequence, can they ask you for the 10th term? And it should be pretty easy for us to find. All we got to do is you got 2, -5 to the 9th, right? Okay. Now, because it's exponential, 5 to the 9th power is going to be pretty big, right? Okay. If we were to graph this, let's see here. I'm just going to graph the ordered pairs there. So it'd be, what, 1, 2. It'd be 2, -10. So the x value is the position in the list, and the y value is the number in the list. So then the 5th one would be 1250. And I could keep doing this. I think the best way to do the rest of these would be, the 6th one would be 2 times -5 raised to the, so 6 power should be to the 5th, right? That makes sense, everybody? Evaluate that. I'm actually going to Control C, Control V. So let's make this a 6. Make that a 7. Okay. Yeah? Not right now. I'm busy. So 8 and 7. Okay. So then, if we look at it, you see, even I go up to an x value of 8, that's a pretty large value, right? But let's look at our graph of these, and we'll have to adjust the the 200. So there's A, there's B, there's C, there's D. You see the distance between A and the x-axis, B and the x-axis, C and the x-axis, D and the x-axis. Those distances, now E and the x-axis, they're getting what to one another? F to the x-axis. G is going to be way up there. Those distances are getting bigger and bigger, right? So if we were to look just kind of at a standard view here, what's happening is that you're getting values like A, and then you're going to go there. Let's kind of do this without axes in here. Without the numbers, at least. All right, so what you're seeing happening is small value, larger, larger, larger. So if we were to maybe connect those, now we don't do this with sequences. Let's look at this as a graph, a connected graph. Oh, that kind of stinks. Your graph is doing something like that. Does that make sense? And now can you view that and that kind of extrapolate and say, okay, what's happening beyond the values I've just checked? Aren't those going to get larger and larger and larger and larger? So we would say if that sequence is diverging again. Does that make sense? Okay. We do see every once in a while maybe a sequence that shows the same behavior if we're to plot them, but it does something like this. We start really high and then get kind of successively closer and closer to some, maybe in this case, the x-axis. So where we say at that kind of sequence of values, if we're looking at the y values of these ordered pairs, that sequence would be converging. Does that make sense? Okay. So those are things that we are interested in kind of analyzing with these sequences. This one here is kind of similar to that. We don't bounce back and forth across the x-axis because everything here is positive. So let's look at those values there. If I look at trying to find an r, okay, so I'm going to take that term there and divide it by that one, right? So 1/3 divided by 1, 1/3, right? Okay. 1/9 divided by 1/3. So 1/9 divided by 1/3. It's 3/9. Is that still 1/3? Okay. I'm going to go same thing here. My hopes are that you can see that the 1/27 divided by 1/9 turns into 9/1, so I'm going to get 1/3 again, right? Can I do this? If I think here that my ratio is 1/3, can I say, okay, now does that 1/3, when I multiply by 1/3, does it give me 1/9? And when I multiply that by 1/3, does it give me 1/27? And multiply that by 1/3, does it give me 1/81? And if I can do it that way, maybe I don't have to do all that division. Does that make sense? Okay. Kind of think this is what I interpret my R value to be. By applying that R value, do I get those successive terms? I think we can do that in all of them. If I think my R value here was -5, can I take -5, apply it to this one to get that one? Can I take -5, apply it to that one through multiplication and get that one, right? Okay. And hopefully we can do that because we understand the relationship between multiplication and division. So now R and this one is 1/3. A sub 1 is 1. So then A sub n should be A sub 1 times R to the n minus 1. Now, because that R value is now a fraction between 0 and 1, we're really doing repetitive division. Does that make sense? Okay. Now, if that R value, so we're repeatedly or repetitively dividing by 3 to get every extra term or every next term. If that was like 2/3, okay, we would be still dividing, right? But because that numerator would be 2, there's still an application, there's still a process of multiplication occurring there as well, right? So those are things to kind of think about as we investigate geometric sequences, and we say that it's always multiplying by some value to get the next term. Well, if that R value is not a whole number or an integer, then there is actual division occurring too. Okay. And then again, obviously, you can find the nth term as much as you want. What I didn't show last class is, but I do want to show you guys what I've done here. I'll just kind of zoom to the first 20 terms of this. I don't know how much you guys have been exposed to Excel, okay, Microsoft Excel, but it allows for the production of your terms in your sequence to be generated very quickly, okay? Basically what you do is you let one column be your n value. So you see that A column there. I just let it be my A values, or sorry, my N values, 1 through, I think I go to 100, 99, okay? But that's really easy to do. If I were just kind of show you how this happens, so I'm just going to identify N, and then I start a pattern, 1, 2, 3. And once I got that pattern, I highlight, click this little button, this little corner, and I just drag it, and it's going to repeat the pattern that I've established as long as I want it to. So if I want to go down to like 110, we see then that it autofills that. Does that make sense? Okay. So then I wrote this equation here. Okay. A sub n is equal to A sub 1 times my R value of 1/3 raised to the n minus 1. Okay. Well, when I type that, I use a specific equation here. So if we look at that right there, I know you might be kind of far away from it and can't really see. Let me see if I can zoom in on that. I don't know if I can change that view. I don't think I can. But that says 1 times. Now this is referencing another cell. It's referencing the 0.33. So I put over there in that blue cell, I put 1/3 in there. So it pulls off that 1/3 every single time. And then it raised to the A sub 2 minus 1. Well, A sub 2 would have been this value here, right? So it's taking my N value of 1 minus 1, which would be 0. So that tells me the first term, tells me my first term should have been 1. Okay? There we're saying now we're going to go back. There's my R value. It's going to go A3, which is this box right there. And so subtract 1 from that. So subtracting 1 from 2 would give me 1. So it tells me my second term. And then once I have that, I can just, again, grab that little corner, pull straight down, and it will autofill those values. So those are my numbers in my sequence. Now, obviously, they're not as fractions, right? Okay, but I get, that 0.3 repeating is 1/3, 0.1 repeating is 1/9, that 0.037 number is 1/27, and then we got 181. The next one, the 0.004, is going to be 1 over 273, and we can keep going on and on and on as far as we need to. Does that make sense? Okay, but you start to see, okay, if we were to plot these N values as X's and these as Y's, what are these Y values approaching? 0, right? Okay, this allows me to go out to 30 decimal places. Let's see if I autofill 109, you start to see that in the 64th term, after that, you don't have any decimal places filled in with non-zero numbers, right? Okay, so if I have to go out to 31, 32, 33 decimal places, Excel only allows you to go out to 30. But you do see it, that is then converging. Does that make sense to everybody? Okay. We'll come back to this and talk about this again here in a little bit when we talk about adding these things together. But that is a sequence in which we are approaching one specific value, and that specific value in that case would have been 0. All right, let's kind of skip through this. Let's talk about partial sums. Okay. Now, like I said, I'm going to skip over this proof work here, but it's kind of showing you the outline of how you would go through about the process of generating these formulas here that I'm going to give you. And this is called the partial sum of a geometric sequence. Again, meaning that I can find any list of values in a particular order that I want to add together, okay, of a geometric sequence. So if I want to add the first 12 terms, I can do that. If I want to add the first 100 terms, I can do that, okay? If I want to add the 13th term through the 40th term, I can do that. I can do a little problem-solving skills, but I should be able to do that. Does that make sense? I can start anywhere in the list I want to and add however many terms I want to together, okay? Maybe we'll do an example of like the 13th through the 30th or something like that here in a moment. But what it says is I'm going to take S sub n, so my sum of n values is equal to A is being your first term, and then 1 minus R to the n over 1 minus R. Okay? The only thing that I need to know there, because it'll be easy for us to find A sub 1, it'll be easy for us to find R. It will not always be easy to tell, what does n got to be? Okay? I'll see an example of this in a moment. Remember, n is the number of objects that you're adding together, right? Okay, we might have to, in some of our homework questions, even with the arithmetic sequences, going to have to play this game here, and I'll show you in a moment, to figure out what n is, okay? There's one on your test that I sent out yesterday that is like this. Okay, so let's do an example. All right, and this is what I was talking about here. 1, 4, 16, 40, 96. Okay? If I want to find, this is geometric. If I look at that, I look at it as a sequence. You don't have to rewrite it this way. But if you look at it as a sequence based off the information that you have, if I take 4 compared to 1 through division, I get 4, right? 16 compared to 4 through division, I get 4, right? So the pattern, because of these ellipses, is going to stay the same all the way up to 40, 96. So what we have to do is we have to figure out what is the sum of this sequence, okay, of these terms. Well, if I look at that, using my formula, S sub n is equal to a sub 1 times 1 minus r to the n over 1 minus r. Okay, what is a sub 1 in this situation? 1. What is r? 4. But do I know what n is? I don't know n, right? I'm having a problem with that. Now, you could do maybe some trial and error stuff, but I'm going to try to pick off values that I want to present to you. That trial and error is going to be cumbersome. It's going to be a problem. You're not going to want to try it. Okay. I might put like 80 terms in between. Okay. There's only a couple here. I think we're missing like 3 terms. So you could do trial and error pretty quickly here. This is how you do it. Okay. If I want to know what n is, I'm adding the nth terms up, right? Well, that's the last term in my sequence that I'm adding together, right? Or my series that I'm adding together. Its position is equivalent to n, isn't it? Okay? So if I can find that object's position, then I know what the n has to be in this summation formula. Well, how can I find that? Think about this. Do you know how to come up with a rule for that? Do you know how to find a sub n is equal to a sub 1 r to the n minus 1? You know a sub n is going to be a sub 1, which was 1, times r. R you told me was 4, right? To the n minus 1. Now, you got 2 variables right now. You got a sub n, that's a variable, and you've got n. A sub n is an object, right? It's the 1, the 4, the 16, the 40, 96. It's those values in those positions, right? Do you know that 40, 96 is one of those values in the position? That's some a sub n, right? Now, if I fill into this formula, a sub n is 40, 96 equals 4 to the n minus 1. Is that an exponential equation that we can solve to find n? And then once I find that, I then will be able to determine what position in my list that 4096 is. How would I solve that? There's 2 ways. You know your power? So with sequences, with geometric sequences like this, if that's 4, think about what we're doing. This was 4 to the 0. This was 4 to the first. This is 4 to the second, right? 4 to the third, so forth. Well, that means that this can be written as a power of 4. Does that make sense? Okay. Well, if you know your power is a 4, which probably a lot of us don't, you could do this. You could rewrite this as 4 to, does anybody know the power? 4 to the 6 is equal to 4 to the n minus 1. And if I've got that, when I got the bases the same, doesn't 6 equal n minus 1? So n would be 7. So this is the 7th object in my list, right? Does that make sense? That's one way of doing it. If you don't know your power, and obviously I think the safest thing, guys, is actually not to use that, because a lot of times, like, what if I get like a 12 there? Does anybody know the power is a 12? No. Okay. So how do I get those exponents out? How do I get those out in front? Take the natural log of both sides, right? Then I can take natural log of 4096 divided by natural log of 4 is equal to n minus 1. You can grab your calculator and evaluate that, but your calculator is going to tell you that that's 6. And your 6 equals n minus 1. That's going to be the most effective way, depending on that base of 4 kind of changing from question to question. Okay? So now I know n is 7. So I can put 7 right there. And now I can just grab one of my calculators, doesn't matter which one. Let's see if I've got Desmos open somewhere. All right, so I had 1 times 1 minus 4 raised to the 7th all over 1 minus 4. We get 5461. Okay. Now, what is nice about this particular problem, because the n value of 7 is pretty small, and I'm only missing the 4th term, the 5th term, and the 6th term, right? Could you take your rule of 1 times 4 to the n minus 1 and find your 4th term? Okay, so you'd find, what, 4 cubed, 64. Okay, you could find up 4 to the 4th. Okay, was that 128? Now 256. And then find 4 to the 5th, 4 to the 6th, and basically finding the terms that are missing inside those ellipses. And now you have all 7. Could you add those together? And you're going to get 5461. Now, the only thing with that, what happens is if I give you, that 4096, maybe just the way the sequence was designed, maybe that's the 100th term. Do you want to find all those 100 terms and add them together? No. Okay. So that formula is going to benefit us when trial and error values start to get very large. Okay. Is everybody okay with that? All right, so we like to talk about, maybe if we have time, I'll show you. Maybe we'll do it tomorrow. Show you how, because we should be able to say if I have a sequence, instead of adding, the first 7 terms up, can we just add the 3rd through the 8th terms up? Okay, we should be able to do that. Okay, but we have to do a little problem solving to kind of generate a plan for that. An infinite series. Okay, an infinite series. Series means that we're taking our sequence and we're just going to put plus signs between all the terms, right? So we're going to start adding these things up. Well, infinite series means that we're going to be adding an infinite number of things together. Okay? All of our summation rules so far, you don't need to write all that stuff down. All of our summation rules right now have that upper bound to be an n value, right? To be a real integer. Okay, a number that we know, okay, or a natural number that we know. Right now, we've changed that to infinity, okay, meaning that we're going to add up an infinite number of objects, okay? Well, when we do that, we run into a problem with our summation formulas, okay, because there's not an n now to plug. I can't multiply by infinity, right? So we'll use some limit stuff in calculus to kind of understand that concept and how we can evaluate and how we change this summation idea here into the formula I'm going to give you in a moment. But what I need you to understand is that an infinite series is just adding up a bunch of things, right? An infinite number of things. And I'll never stop adding those things together. What you need to understand, though, if I add an infinite number of things, the mind wants to think, well, if I'm adding an infinite number of things, my sum is always infinity. Do you agree that your mind wants to think that? Okay? That's not the case. Okay? And I'll try to explain that when we go back to that Excel sheet in a moment. We have 2 situations. Okay? When we are taking a geometric sequence and we're adding up infinite things, we have a potential of getting a sum in which that sum converges to one value. Okay? When we see that like 1/3 to the n minus 1 sequence, that's going to sum to 1.5 as I add up infinite terms in that thing, okay? If we look at that one that was negative, I think it was negative 5 to the n minus 1 or whatever, 2 times negative 5 to the n minus 1, that one is not going to sum to a particular value. That summation, as we move on and on, we're adding larger and larger values as we get further and further out into the sequence or series, and that sum then diverges. It goes off to infinity, okay? So those are the two issues that we have. We have the ability to converge, and we have the ability to diverge, okay? We like to be able to analyze easily what is occurring. So the first thing we have to do is realize what is our sequence. Is it geometric? So once we say it's geometric, we then look at our common ratio, okay? If our common ratio, okay, if its absolute value is less than 1, okay? And when I say absolute value is less than 1, hopefully you guys know, you realize that that basically means that my R value is between negative 1 and positive 1, okay? If I'm between negative 1 and positive 1 for my R value, then we have what we call a convergent series, and we're going to be able to converge to a sum, and that sum is actually a really nice formula. It's A divided by 1 minus R, okay? If my common ratio is outside that range of values, okay, so it's bigger than 1, or it's more negative than negative 1, then we have a divergent series, and it's going to go off to infinity when we start adding the values up. Okay? So when we look at these, do an example here. Okay? Actually, let's just use the example that we've already seen and I've got set up in Excel. We had A sub n was equal to 1 times the third raised to the n minus 1, right? Okay? So the question would be, they would show you, they'd say 1, 1/3, 1/9, 1/27, ... and they'll ask you, is this series, if I were to put plus signs in between those, is it divergent or convergent? Okay? First thing we have to do is it geometric? Yes, it is geometric. We know that R, and we're able to find R, we know that's 1/3, right? Is the absolute value of 1/3 less than 1? Yes. Okay? So this thing converges. Mess that up. This thing converges. Converges means it moves down to one particular value, right? Okay? So it converges. So then it converges, we can then say, well, that sum is going to be equivalent to that thing right there. So we take our A value. What was our A value? It's A sub 1, right? It's your first term. So I take 1, I divide it by 1 minus R. Well, that's 1 over 2/3, right? 1 over 2/3 turns into 3/2, right? Or 1.5. The reason for this, the reason this happens, think about if we go back to this, think about these positions. Now, if I were to add straight down, okay, let me zoom in on maybe just to make this a little bit bigger for you. View. If I add straight down, I'm adding these values of 3, 1, and then all these things down here are zeros, right? Okay. If I add straight down the hundredths column, it's 3, 1, 3, 1. Okay. And then straight down. And I keep doing. Now, there's going to be some carryover eventually. Okay. But look at what we're doing as we're moving from larger and larger values of n. I'm just adding eventually to the end of my or more decimal places to the right. Does that make sense? Okay, so this decimal place right here, this 17197 right there, isn't going to impact this 0.3. Okay, so I'm adding values that are eventually getting smaller and smaller and smaller. So if I were to sum all these, so I'm going from B2 to B10 or 110. So let's go right. So that equals sum of B2 to B110. Okay, so add all those together, and you see that it's going to give me Now I only got 29 decimal places after that 5 there, so it's seen then that we're getting a sum very, very close to 1.5. Does that make sense? Okay. We'll talk a little bit more about this tomorrow.